All right, welcome back everyone. So if you're watching this video, we must be closing in on our second exam for Chem 151. So what I have here is the sample version or practice version of the second test. You can find a copy of this test on your Moodle site for the class. I would highly recommend that you try out the practice test, see how well you do before you come back and watch the answer key. So if you haven't tried it yet, maybe pause, go try the problems and try to work them out on your own before you come back and see how I work them out, or double check your answers. That gives you the best mimic of how the test is going to be, right? When it comes to test time, just like the first test, you can have your periodic table, you can have your calculator, right? But outside of that, you need to be able to kind of look at these problems and figure out what to do just from the information provided. The best way to practice that is to practice that, to do a sample run through the test and see if you really are prepared for addressing the problems of this type. So if we jump right in here to the first problem, we've got a 2.74 gram sample of a substance. So right off the bat, there's a mass. And we suspect that this might be gold, right? But to find out, it looks like we're going to do a thermodynamics experiment. So we warm this sample to 72.1 degrees C, and then we drop it in 15.2 grams of water. That is at a lower temperature, 24.7. So hot object coming in contact with a cold object, that means there's going to be heat transfer from the hot to the cold. So after the heat is transferred, the final temperature of both the metal and the water is 26.3 degrees C. There's enough information for us to calculate temperature changes, right? Is the substance gold? And what we're given here is the specific heat capacity of gold. That's there for comparison purposes, right? What is not here in this problem, but is something that I do consider something I would provide on the test, is the specific heat capacity of water. And that'll be relevant to solving this problem. Now, I kind of hope at this point, if you're watching this, you've probably practiced enough of these that you should remember the specific heat capacity of water, because it comes up all the time, and it comes up when you're converting from joules to calories, if you have to do that, or calories to joules. So you probably should know that, but just to be clear, we will need that information in the problem. Now, the other thing that we need to kind of realize here for this problem is because heat is transferring, we're going to have a quantity of heat that is lost by the metal in this case. And the way we set up these problems, we set this experiment up so that all the heat lost by the metal is going to go into the water sample. And what that means is if we can calculate one of these quantities, we then know what the other one is. So in this case, if we can calculate how much heat went into the water sample, we know how much heat came out of the metal, and that will help us determine what the specific heat capacity of the metal is. So if I want to calculate the heat that goes into the water, there's an equation that relates heat to specific heat capacity, mass, and the temperature change. So heat, or Q here, is equal to the specific heat capacity of the water times the mass of the water times the temperature change of the water. We've got all of that information. So specific heat capacity of water again is 4.184 joules per gram degrees C. We want the mass of our water sample in grams, so be careful. That's a common trick you can use in the problem, is to give you the masses in some other measure, kilograms maybe. It is grams here in the problem, 15.2 grams of water. And there is another mass there, so make sure you're finding the right one. There's a mass of metal and a mass of water. Delta T, temperature change of the water. Now, the water started at 24.7 and ended up at 26.3. So the difference there, I'm going to use my calculator because I've found I'm making silly mistakes trying to subtract in my head lately. The difference is just 1.6 degrees. Now, keep in mind, that's two significant figures. That will probably limit us somewhere, right, along the way. Now, in this case, we're just trying to figure out if it's gold, so we don't really have a numerical answer. But right, the way we'll know it's gold is if it has the same specific heat capacity. Okay, joules per gram degree C times grams times degrees C. Everything is going to cancel there except joules, and that's appropriate since that's how we describe heat. So multiply this out. 4.184 times 15.2 times 1.6, and that is 101.75 joules. Now again, we really just have 2 sig figs, but I'm going to save some extra data there to avoid rounding errors, because this is the heat that went into the water. This is going to be part of our next calculation. The way we set the heat into the water is equal to the heat lost by the metal. This will also be equal to how much heat was lost by the metal. Right? So now, in terms of the metal, we know the heat that came out of the metal. We know the mass of the metal from earlier in the problem. Right? And we have enough information to figure out the temperature change of the metal. So taking this same equation relating heat, specific heat, mass, and temperature change, but rearranging it to solve for specific heat capacity, the specific heat capacity of this metal will be equal to the heat that went into the metal divided by the mass of the metal and the temperature change for the metal. Right? So unit-wise, joules per gram degree C. Right? So the formula, of course, matches the units we're using to describe that quantity. So the heat is 101.75 joules. The mass is 2.74 grams. Right? And the temperature change, again, we do have to calculate. So the temperature of the metal started at 72.1, ended up at 26.3. Now, the kind of formulaic way to calculate temperature change is to take the final minus the initial. In this case, that would give us a negative number, right? That's fine, that can be a negative number, but if we use a negative temperature change, that means we should also use a negative Q here. Like we've talked about before, I usually avoid the negatives by using the descriptions of whether heat went into something or out of something. So heat that's lost, you could also say is negative, right? But in this case, I'm going to subtract to get a positive number. Because I kept a positive for Q. Nope, it's not 24.7, it's the 26.3, the final temperature that we need there. So 72.1 minus 26.3 is 45.8 degrees C. That's our temperature change. That goes in the bottom there of that relationship. Now if we work all that out math-wise, none of those units are going to cancel. So this will give us joules per gram degree C. That's exactly what we want for the units describing specific heat capacity. So 101.75 divided by 2.74, right? And the 45.8 is still on the bottom, so I also want to do divided by 45.8. Right? That's actually a common math mistake that people make with this type of problem. If you punch this in a little carelessly, you can end up multiplying by 45.8 instead of dividing this number by 45.8. So either be careful how you do it or use extra brackets if you need to get it punched in right. This comes out to be 0.81 joules per gram degree C. And again, I rounded to 2 because of our temperature change back here, right? But this makes it clear that this is not gold. Up in the problem, we were told the specific heat capacity of gold is 0.128. We got 0.81. That's a pretty large difference from the specific heat capacity of gold, so this is not gold in our sample. In fact, this is probably aluminum. That's pretty close to the value for aluminum, which we've encountered in some of the problems that we've practiced. Now, I think that's the most straightforward way to do the problem, just determine the specific heat capacity of the mystery metal. You could also use this specific heat capacity. Since you know the mass of the metal, and you know the temperature change with the metal, you could use this specific heat capacity, and if that was the case, what you'd be calculating is how much heat would gold have had to lose to cause the rise in temperature we saw in the water. And you would find out the quantities of heat don't match. The amount of heat that went into the water would be different from the amount of heat that would have come out of a sample of gold had it lost that temperature that is described. I don't think that's quite as direct of a way to kind of analyze the problem, but it is a way you could analyze the problem as long as you're keeping track of all your units. Okay, so keep that in mind. There will almost certainly be a problem related to these heat transfer equations, right? And maybe one where the heat is going in two directions like this one, where you'll have to kind of compensate for that. Okay, we'll stop that video there. We'll pick up with question number 2 in the next video.